The HR diagram is the most important tool in the astrophysical concept of stellar evolution. Each part of it tells its own unique story. We will be exploring this diagram in this video. The diagram is a plot between the luminosity of a star and its corresponding temperature. A star begins its journey in the HR diagram as a protostar.
A protostar is a very young star that is still gathering mass from its parent molecular cloud. The protostellar phase is the earliest one in the process of stellar evolution. For a low mass star, it lasts about 500,000 years. The phase begins when a molecular cloud fragment first collapses under the force of self gravity. A protostar looks like a star, but its core is not hot enough for fusion to take place. The luminosity comes exclusively from the heating of the protostar as it contracts. These are usually surrounded by dust, which blocks the light that they emit, so they are difficult to observe in visible spectrum. A protostar becomes a main sequence star when its core temperature exceeds 10 million Kelvin. This is the temperature needed for hydrogen fusion to operate efficiently.
But what happens if the initial mass of the star is not enough for gravitational contraction process to occur? That's when a brown dwarf forms.
A brown dwarf star is a substellar object whose mass ranges between that of giant planets and small stars. Its mass is too low for it to fuse hydrogen, as main sequence stars like our Sun do. Brown dwarf can be thought of as a kind of missing link between planets and stars. The successful formation of a star leads to star entering the main sequence.
Main sequence stars are the most common type in the universe. Main sequence stars are stable, they fuse hydrogen nuclei together to form the helium nuclei, releasing energy and emitting light. A main sequence star is a star in the stable part of its life cycle. They are the most common type of star in the universe. Our star, the Sun, is in the main sequence phase. It is about halfway through this stage and ultimately will become a red giant in roughly 5 billion years. The main sequence stage occurs after a stellar nebula collapses due to the force of gravity. As the nebula collapses, the internal temperature increases. When the core of the newly formed protostar reaches a certain temperature, nuclear fusion starts. Nuclear fusion is a nuclear reaction that releases energy by fusing together smaller, lighter nuclei into a larger, heavier nucleus. This process releases photons of energy. These photons are absorbed and reabsorbed multiple times before leaving the star. The amount of energy that is released can be calculated using the Einstein's equation E equals to mc square, where E is the amount of energy, m is the change in mass, and c is the speed of light.
Sometimes my genius, it generates
photons.
Most main sequence stars are nearly completely composed of hydrogen and helium. Some have a small percentage of heavier elements such as carbon or oxygen. Scientists can analyze the composition of a main sequence star by studying the light they emit. All main sequence stars are in equilibrium, meaning the outward pressure caused by the fusion reactions is balanced by the force of gravity pulling the star together. The pressure and temperature of a main sequence star increases as you get closer to its center. The length of time that a star spends at this stage in its life depends on how much mass the star has. Counterintuitively, massive stars have a shorter lifespan than small stars. Large, massive stars use up their nuclear fuel at a much faster rate than small stars. Stars can range in size from about a tenth of size of our sun all the way up to 100 times as big. The color of a star also varies depending on its size. Larger stars are hotter and they emit more blue light. Smaller stars are smaller and emit more red light.
At the end of the main sequence, the star is almost completely out of hydrogen and is filled mostly with helium. However, The core temperature is not high enough to burn helium. As a result, there is no nuclear energy to sustain the gravitational energy. As a result, the star starts collapsing. This generates energy, heating up the outer shells of the star in the process. This heating causes the outer shell of the stars to expand. Burning in the outer shell also contributes to the increase in the luminosity of the star. This increase in size and luminosity forms the red giant.
The core of the red giant is extremely dense, and in initial stages, core compression continues due to lack of energy generation, increasing the temperature to higher than 100 million degrees. This high temperature results in formation of carbon, nitrogen, and oxygen. These reactions result in the release of nuclear energy, which causes an increase in temperature. In red giants, at extremely high temperatures and densities, electrons are squeezed together to a limit when Pauli's exclusion principle comes into play. However, pressure doesn't increase with temperature and hence no expansion occurs. The increase in temperature increases the nuclear energy generation rate to the point where helium flash occurs. Post the helium flash, the core and shells cool rapidly and luminosity decreases. Rapid contraction occurs, which causes a rise in temperature and reignition of helium. However, the core is not dense, so the flash does not reoccur. Rather, helium is burned to carbon and oxygen that occupy the core.
Post the red giant phase, the star will follow two paths depending on its mass. If the mass of the star is below a particular limit, events follow that result in the formation of a white dwarf.
These ancient stars are incredibly dense. A teaspoonful of their matter would weigh as much on Earth as an elephant, 5.5 tons. White dwarfs typically have a radius just 0.01 times that of our own sun, but their mass is about the same. The planetary nebula phase is a final stage in a low mass star's life. During this phase, the star sheds its outer layers. This creates an expanding, glowing shell of very hot gas. Despite the name, they have nothing to do with planets. They got their name because astronomers using small telescopes long ago thought that they looked a bit like planets. Low mass stars turn into planetary nebula towards the end of their red giant phase. At that point, the star becomes highly unstable and starts to pulsate. This produces strong stellar winds which throws off the outer layer of the star. The outer layers drift away from the star, leaving a small, hot, bright core behind, called a white dwarf. The white dwarf gives off ultraviolet radiation, which lights up the layers of gas around the star. Over time, the material from the planetary nebula is scattered into space. Eventually, it will form part of the clouds of dust and gases where new stars form. A supernova is the name given to the cataclysmic explosion of a massive star at the end of its life. It can emit more energy in a few seconds than a sun will radiate in its lifetime of billions of years. The sky above us is strewn with alluringly beautiful remnants of ancient supernova, that is, stars that lived out their lives and then died in these violent explosions. In a galaxy like our Milky Way, consisting of some 200 billion stars, there should be a supernova as often as every 50 years. Yet supernova visible to the eye alone are exceedingly rare. You might or might not witness one in your lifetime.